Hello everyone. Today, I'd like to present our research titled, ConDefects, a new dataset to address the data leakage concern for LLM-based fault localization and program repair. Now, let's dive right in. Our core contribution lies in the creation and release of a new dataset called ConDefects, sourced from @Coda. A distinguishing feature of our dataset is the timestamping of each coding task. This allows researchers to selectively pick data based on time, optimizing the data selection for specific LLM models. To facilitate this, we've developed a toolkit. It doesn't just allow for time window selecting based on parameters but also offers features to view dataset details and even execute or collect statement coverage information. Alright, shifting gears a bit, let's talk about the impact of LLMs. The emergence of giants like ChatGPT has indeed paved the way for groundbreaking applications in software engineering. Areas like fault localization and program repair? Well, they're no exceptions. As we'll explore, numerous research initiatives are eagerly capitalizing on ChatGPT, showcasing its ever-growing potential in this arena. One of the remarkable strengths of ChatGPT lies in its ability to infer and understand code. Imagine handing a piece of malfunctioning code to ChatGPT. More often than not, ChatGPT seems to discern the intended purpose of that code segment. It's almost like chatting with a seasoned developer. Then it can find the position of faulty statement. But it doesn't stop there. ChatGPT can not only pinpoint where the mistake is, it can even rectify it. Additionally, there have been endeavors where researchers presented ChatGPT with incomplete code snippets, essentially saying, "Here, you finish this." Indeed, coding challenges hardly seem to bother ChatGPT. Current studies attest to this, showcasing truly impressive results with ChatGPT at the helm. To assess the might of ChatGPT, existing research has pitted it against time-tested datasets from the realm of fault localization and program repair. Names that might ring a bell include Defects4j, Manybugs, CodeNet, not to mention code snippets from familiar platforms like GitHub and Stack Overflow. These datasets served as the battlegrounds to evaluate ChatGPT's prowess in fault detection and code rectification. However, here's a crucial caveat I must stress upon: these datasets, they might have already been eaten by ChatGPT. Specifically, OpenAI's data collection cutoff for training ChatGPT was September 2021. The inception of many of these renowned datasets predates this cutoff, implying that they might have been incorporated within ChatGPT's training regimen. This inclusion potentially grants an inadvertent advantage to ChatGPT-centric evaluations. Recognizing this disparity, we embarked on gathering a novel dataset. Our mission? To provide a fair playing field for assessing LLMs. Next, let's delve deeper into the processes of our dataset, how we filter, collect, and label the data. Our primary data reservoir is @Coda, a prominent programming exercise platform. The audience it caters to is vast, ranging from professional developers and students to individuals from other disciplines. One might ask, why @Coda? Well, we were drawn to its original coding tasks and high activity level, ensuring both the timeliness and quality of data extracted from this platform. It's also noteworthy that various other datasets have sourced code from @Coda for diverse research domains. Starting with our selection criteria, ConDefects exclusively incorporates coding tasks published post-September 2021. By doing so, we ensure that our dataset stands as a distinctive and current benchmark tailored for contemporary LLM evaluation. Additionally, in our pursuit to align with well-regarded datasets in our field, ConDefects specifically emphasizes Python and Java programs. Let's discuss the data collection phase. For each task of user submissions, we sort the code in reverse chronological order to determine the final accepted answer, abbreviated as AC. By analyzing earlier submissions in this reversed order, we can methodically trace the progression of code submissions from individual users. From this analysis, we can pinpoint submissions marked as wrong answers, WA, which only need a one-line modification to be fixed. Such WA submissions are collected and labeled as the faulty programs in our dataset, and the corresponding AC serves as the correct version. We label the location of this single-line difference as the location of the faulty statement. The primary goal behind this method is pinpoint the exact location and corrected version of the faulty statement in each program. To align with many fault localization and program repair studies, we specifically curate our dataset to include only those programs that have a single faulty statement. It's also important to highlight that if a coding task's submissions do not meet these conditions, such as no WA or AC submissions, or no WAAC pair that satisfies the conditions, these codes will be excluded from the dataset. This ensures the integrity of our labels and removes any potential for unclear or misleading data. Moving on, let's delve into the specifics of the data we've amassed. Our focus is on the date distribution, statistics, and difficulty distribution. Among these, date distribution holds a special place in our hearts, primarily because our initial goal was to prevent data leakage issues in LLM-based methodologies. Beyond the dataset cutoff for ChatGPT in 2021, there will inevitably be the advent of more LLM models. Predicting the exact training data timeline for every future LLM is impossible. Therefore, to make our dataset versatile for subsequent LLM models, we've diligently tagged each code with a timestamp pertaining to its respective coding task. By anchoring to the coding task's release time, we ensure that any code birthed aligns with a specific timeframe, preventing it from predating certain points in time. As shown in the following chart, we present the time distribution of coding tasks. Additionally, we've equipped researchers with a user-friendly tool for selecting time window based on their timestamps. This makes our dataset particularly apt for studies sensitive to dataset publication timelines. The details of the code in our dataset can be seen in this table. Each faulty code is paired with labeled fault locations and their corresponding fixed versions. This makes our dataset highly beneficial not just for LLM-based studies but also for traditional fault localization and program repair research. Moreover, to assure diversity in our data, let's turn our gaze to this graph depicting the difficulty distribution across coding tasks. This graph enlightens us on the various coding task difficulty categories. Such a wide-ranging difficulty spectrum guarantees objective evaluations, acting as a bulwark against overfitting or biased modeling. In essence, our emphasis on diversity is a proactive move to stave off overfitting. Wrapping up, let's get acquainted with our highly intuitive toolkit designed for seamless user engagement with our dataset. At present, this toolkit boasts 4 primary features: meta information, dataset checkout, execution and test case report, and coverage collection. Let's kick things off with deployment. Begin by checking out the code from our GitHub repository. Next, according to the instructions detailed in the README, download the corresponding test cases for the data. Then place the compressed package of the test case in the root directory of the checked out code. Your file directory should ideally resemble what's showcased in the upcoming picture. The star of the show here is the ConDefects.py, the grand entrance to our toolkit. Once you've followed the requirements from GitHub and set up the Python and Java environments, you're all set to roll. First up, the meta information feature. It's your go-to for a quick glance at the dataset's essentials. With the list tasks command, you get a grand view of all available coding tasks in the dataset. The test cases command, when accompanied by a specified coding task name, graciously reveals the list of test cases linked to that particular coding task. Diving deeper, the program command, in cahoots with a designated coding task name and programming language, displays executable programs under the specified coding task. And yes, those numbers on the left. They're unique identifiers for each program. Lastly, the program ID command, when paired with the unique program number, unveils the program's directory location, the error statement's line number, and the intricate details of both the faulty and corrected code housed in that location. Now, let's shift our focus to the Dataset checkout feature. This tool lets users handpick specific programs from the dataset according to their needs, and swiftly funnel them to a designated directory. A vital aspect to remember is the obligatory W parameter, which signifies where you want these selected programs to be directed. Should you choose to operate with no additional parameters, executing the command would channel all coding tasks and their associated code to the aforementioned directory. However, to refine your selection, we've equipped the tool with a myriad of parameters, which can be leveraged in any combination to hone in on specific coding tasks. First up, we have T. By following this parameter with 2 date strings, you can sift through coding tasks that were launched within that specific timeframe. Next, D comes into play. By inputting 2 integer values after this parameter, you can cherry-pick coding tasks falling within the designated difficulty range. For those looking to zero in on a single coding task, S is your go-to. Moreover, recall how our dataset houses programs in both Java and Python. Well, the L parameter allows you to earmark one of these languages. By doing so, your filtered dataset will be streamlined to solely encompass programs in your chosen language, offering you tailored data at your fingertips. Let's turn our attention to the execution and test case report feature. With this at your disposal, you can effortlessly execute the code you've gleaned using the checkout feature, and subsequently peruse a report detailing the outcomes of the test cases. An indispensable parameter here is W, which designates the location of the programs you intend to execute. If no additional parameters are employed, the toolkit, by default, runs every code segment, generating a detailed report for each, as illustrated. This report encapsulates the outcomes of individual test cases, along with an overarching pass rate. Furthermore, if you desire to hone in on a specific coding task, the S parameter is at your service. Alternatively, the T command empowers you to specify a set of test cases for execution. Venturing into the coverage collection feature, it comprises all the parameters embedded in the execution and test case report feature but necessitates an additional O parameter. This serves the pivotal role of storing information about statement coverage and test cases execution outcome. At the directory defined by O, for each program, you'll find 3 crucial files. Statement coverage information, where each line corresponds to the coverage for a test case, with 1 signifying that the specific statement in the program was executed, and 0 denoting otherwise. Test case execution outcomes, indicating success with true and failure with false. A list of executed test cases that align with the 2 preceding files. With this toolkit, we aspire to streamline the process for developers as they embark on research in fault localization and program repair, leveraging our dataset. As an added note, we've juxtaposed the Java code from our dataset with the fault localization outcomes derived from the SBFL method in Defects4j. This comparison revealed stark discrepancies in the top-end results. Such a revelation underscores the imperative of utilizing a diverse array of datasets to holistically evaluate fault localization techniques. That concludes the main content of our work. We eagerly anticipate your use and feedback, hoping it can facilitate your research and tasks. Thank you for taking the time to engage with our presentation, and wish you success in your endeavors.